Okay, my name is Benny Verza, and I would like to present to you about the Foucault pendulum. And I just want to start with the question of, does the Earth really spin? This is not a trick question. The answer is yes. We do know this now. It's pretty trivial. But if you go back even a couple hundred years, for example, Copernicus, all of his works were declared heretical, because he declared that maybe the Earth is not the center of everything, and in the end he was right. But it does kind of seem that everything goes around the Earth. If you track, for example, the path that stars take, they seem to go around the Earth on an axis. If you look at the sun and the moon, they seem to pass around the Earth. So one interesting experiment that you can do to show that it's the Earth that's spinning and not everything else is the Foucault pendulum. And so I want to talk a little bit about the history of the pendulum, and then about the physics, and then go into the actual building process. And first, I want to start with the creator, which is Foucault, who was a French physicist who actually started out as a physician. And interesting enough, he is more known for his various optics stuff, because at the time, one of his biggest things was that he predicted the speed of light to the most accurate degree at the time. But I want to talk more about his pendulum, which, interesting enough, is not initially his idea. It was first done by an Italian scientist, Vincenzo Viviani. And the purpose of the pendulum is to show something called diurnal motion, which is a fancy way of saying that it's not everything spinning around the Earth, but it's rather the Earth spinning and the effects out of that. So Foucault initially started out making smaller pendulums in his house, but over time, after he showed it to more and more people, the experiment gained popularity, eventually reaching the Pantheon of Paris, where there's a 67-meter-long pendulum with a 28-kilogram bob at the bottom. And so to understand the pendulum, you need to understand non-inertial reference frames. But I want to start with inertial reference frames first. So here is a little animation, and you can see that since the little stick guy and the cart are moving constantly, both observers, which is to say everyone looking at this video and someone on the cart, would see more or less the exact same thing. The stick guy would jump and then land back on, everything's fine. In a non-inertial reference, here you go. For example, you can see that while he jumps, the speeds are the same, so he lands perfectly. In a non-inertial reference frame, for example, if the cart is slowing down, you're now going to see different things from different perspectives. From our perspective, we can see that while the stick guy jumps off, the cart then starts to slow down, and then he lands off the cart. But from the perspective of the cart, it looks more like the stick person is just jumping off the cart. And this is essentially where you get non-inertial reference frames. It's whenever there's an acceleration and observers disagree. So the Earth is a big spinning ball. And because of that, at any given time, your velocity is changing where you're going. So there is an acceleration. So the Earth is one big, giant inertial or non-inertial reference frame. And the consequence of that is you have these three forces, the centrifugal, the Coriolis, and the transverse force. The only one that matters for this experiment is the Coriolis force, which you may know for influencing like weather patterns. So you can imagine that from space, so from this picture, if you were to have a pendulum swinging above the North Pole, it would just be swinging in one plane, and the Earth would rotate under it. But if you were to be standing next to the pendulum, it would look like the pendulum itself was turning. And here is a video from a student, Lambeau, who worked on this project in 2021, showing how the pendulum turns. This is over 6 hours, and it's pretty clear that it is turning. So I want to just get into what I did with this pendulum. And so the first thing I want to talk about is the actual parts of the pendulum. And we have this 2-meter long wire and this 4.5-kilogram bob at the bottom. This is not the difficult part of the pendulum. Because this, Foucault did this 300 years ago. This is not a very big deal. What is a big deal is that we are trying to drive it essentially forever. So that we could maybe put it on display or something like that. And what we're trying to do is use this, which has these two lasers intersecting perpendicularly, to find where the pendulum, or when the pendulum is crossing through the center. And then we're using an electromagnet and this metal cylinder attached to the wire to give the pendulum a little nudge every time it passes through the middle so that it can be driven forever. And we're doing that with this power supply and circuit, which essentially, as soon as the two laser beams are blocked, that means that the wire is crossing through the middle, and so we activate the magnet for a little bit of a time. It pulls the little metal cylinder, and then it keeps going. And lastly, we've got this little array of sensors, which are not for anything in the pendulum itself, but we're using it to keep track of where the pendulum is. At the tips of these sticks, we have magnetic sensors, and at the bottom of our pendulum bob, we have a little magnetic cube. So whenever it passes over these sensors, we get a voltage output, and the stronger the voltage output, the closer to the center it is. So here's some data from a 90-hour reading, and as you can see, each color is a different sensor, and we have 9 of them. This is not very readable, so let's just take a look at one sensor here, for example. So what we're measuring here is the time to go through different degrees. So our slope is going to be this precession rate of degrees per hour, which, as you can see there, is about 11.6. And so naturally the question is, well, is this correct? From an equation that we can derive, we can take the latitude of the Earth, interestingly enough, to be theta, and omega here would be the rotation speed of the Earth. And then omega z would be the rotation speed of the pendulum, or what we expect. The latitude we're at is about 42.3, which implies that we should have a precession rate of about 10.1 degrees per hour. That is clearly not the same as 11.6, so we have to figure out, well, what could be going wrong? The first thing I considered was maybe the wind resistor or air currents or something like that was getting in the way. So which is definitely plausible, although they may seem very minimal. The Coriolis force itself is not very strong. So I put up this big plastic sheet to block any wind currents. But while doing that, I nudged one of these lasers in the drive, and all of a sudden the pendulum was not driving anymore. I looked a little bit closer, and what you'll notice here is that these lasers are screwed directly into the mounting plate. That's not great because you don't have the ability to adjust it anymore. And the way that it was set up previously just happened to work, but it was not screwed in all the way, so it's not extremely precise. So I decided to take everything down, and I could swap out the mount for these mirror mounts, which have these 2 knobs, and you can adjust the different axes that the lasers are at. So essentially, we're not going to have any alignment issues, since we can always change it no matter what's going on. But what you may notice in this picture is there is no longer a magnet. And the reason for that is that while I was taking all of this down, one of the terminals on the magnet came off, which is one of the ends of the wire. And so I tried to open it carefully to find where this end was. And unfortunately, this is a very old magnet, so all the wires exploded everywhere, and it was gone. For the time being, we tried a couple different other driving methods with different magnets that we happen to have. As you can see over there on the left, we tried to use a big ring magnet through the middle of the pendulum, and you can see here on the right, we tried to use a resonance to push it. Neither of these really worked, so we decided that we ended up needing a magnet in the end. As it turns out, it's kind of difficult to find a magnet to the specific properties we wanted, so I figured I could try making one myself. I took a day and I wrapped about 5,000 feet of wire by hand, and I attached it maybe somewhat precariously to the mount. So what is the end result? Well, here is one of the graphs from after all of the work I did, and you'll notice that the slope is 8.2, which is still not 10.1. So what does that mean? Well, since you can take the latitude as a function of how long it takes to go around, initially we're somewhere in Canada, and afterwards we're somewhere in Alabama. And I'll just remind you, we're somewhere in the middle. So what could still be going wrong? The first and biggest issue is that I was the one that wrapped the magnet. I'm not a robot. I'm not a perfect magnet-making machine.
You're being pretty good.
I appreciate it, but there's almost certainly imperfections. There's almost certainly inconsistencies on the magnet, so it's definitely causing problems. Another issue could potentially be with our equation itself. What we're using for our equation is the small angle approximation, which really only works for small angles. And the question of how small depends, but our pendulum swings about 3 degrees, which very well could fall outside of this range. Another issue that could be causing this is additional forces. We have a ring that the magnet is hitting whenever it hits the mount, or not the magnet, but the wire is hitting this magnet, or the magnet is hitting this ring every time it goes around. And that could cause a small frictional force that could also mess with it. So there's a lot of things that could be at play, but it's also very possible that the way we're driving it is not great. There have been some papers that indicate there are better ways to drive, and as I showed, 2 other methods that didn't seem to work. But that's not true that all methods won't work, and it's very possible that there are other methods that we could try that could work out better. And that's all I've got for you today.